Hello, everyone. Good afternoon. So I work with Professor Ambarish Ghosh in Indian Institute of Science. And today I'll be talking about development of all magnetic active matter, specifically how to have the reciprocal swimmers and non-reciprocal swimmers in such a system. We have heard the talk just now. So active matter system is a system where there are many components, and each component is always out of equilibrium because there is always some intrinsic energy dissipation or consumption. And this is quite a very popular phenomenon. You'll find it everywhere in nature, and when they are in large numbers, you see they produce very beautiful patterns like what you're seeing over here. But today, what I'll be discussing is the system at a very small scale. So when I say small, so how small? So we define a number that is Reynolds number. So the Reynolds number is nothing but a ratio between inertial forces and viscous forces. But at a very small Reynolds number, the inertial forces is completely negligible. We can ignore it, and hence the dynamics of the body is completely governed by the inertial forces, viscous forces. So this is the range at which I'll be talking about. That is at a very low Reynolds number. So you might relate it better when you see these kind of videos. So the bacteria there, and here the sperm swimming in the fluid. So these are the classic examples which are available in nature, which are at low Reynolds number. But my system today is not a natural system. We try to make an artificial system which kind of tries to imitate what is happening in these natural systems. So in our case, the system we have is of micron scale, and the energy input is coming from a magnetic field. These helical structures have permanent magnetic moment to them. So because of the external magnetic field, they kind of respond to the energy input, and then there is locomotion in the fluid. Now, what exactly happens is that, suppose I'm giving a 3D rotational field in XYZ direction. So it means that it has a specific directionality, and hence these particles move in a given direction. But that's not exactly what we want, because in case of an active system, we want these particles to be randomly moving around. But there's also an energy input. To make them, to make their direction randomized and not just, point them in a particular direction and just drive them there. So what we do is we just replace the magnetic field with an oscillating field. So if you have just an oscillating field in a single direction, you see that the swimmer will just try to go back, try to go forward and then backward in time, and it just keeps on doing it as and how you keep oscillating your external field. But there is a small caveat in all of this. It is that so when we discuss about motion at small Reynolds number, we cannot escape something called Scallop Theorem. So what is it? Is that if you take the Navier-Stokes equation, and if you just remove all the inertial terms, then you are left with an equation which is symmetric in time. And what does it mean is that if you see on the right hand side over there, so if you deform your body in such a way that you keep doing a symmetric kind of a sequence, that is when you're going from A to A and then you go back from A to A, it's the same thing in time. So you cannot really differentiate what is happening. But instead, if it is something like this, so where you go from A to A, it is something else. But again, when you're coming back from here to here, it is a different set of deformations. So to have a net displacement in low Reynolds number, this is the case that is preferred and not this. Because if the organism keeps doing this, it's not going anywhere. And hence, in all the natural systems, this is how they actually achieve their locomotion, by doing this kind of a sequence. So how does it relate to our system? Well, in our case too, I was just trying to give some oscillating field in in one direction, and then they were just going backward and forward. So in our case, this kind of there's no deformation, but it is something called, we call it as turning. So it just means that in the forward direction, it's just turning in the clockwise, and then when it's coming back, it's turning in the counterclockwise. So it keeps doing that like forever. So you just have this kind of sequences, and we don't want that, because if you have that, it's you're not really going to achieve much displacement in the system, and it's not really a very good active system. So how do you break this? Like, how do you make sure that this is not what it does? So what we saw was interestingly was that when we were actually giving the magnetic field this way, this turning statistics like significantly depended upon how fast or slow you are basically switching your field. So how fast you're going from B to minus B, or the vice versa. So when we actually plotted that just by numerically, so we saw that at very small, at very long time scales, which means if you turn it very slowly, so it always took the desired turn. So it always went ahead, and then it again came back. But then if I started switching the field very fast, like if I started oscillating it basically very fast, then we saw that it preferred a certain turn. So it might be like there were more clockwise turns than the clockwise and counterclockwise turns, which is to say that, so so in the previous diagram where I showed you, it was just that there were equal number of turnings, but now there are more clockwise turns compared to the counterclockwise terms, or either way. When we saw this when we saw that it happened this way in experiments, and then when we also cross correlated it with our numerically predicted graphs, we were confused that why is it happening? Why is it this time scale mattering? Then actually we went to the energetics of the system. So if you see over here, this plot, we have plotted this energy diagram for a single swimmer. So when it is trying to basically go from some plus B to minus B. So if you carefully see this diagram, so currently if my swimmer, if there is some positive magnetic field in the system, and if I change it to say a negative system, it basically just does a clockwise turn. It just takes some clockwise turn, and it comes back to this curve here. Now I just stay here for a while, and then I immediately, change the time, basically change the field from minus B to plus B with some time. So yeah. So now when it is over here, now the particle is going there. So what happens even in the energy diagram, if you see, it basically goes above. So now the particle is over somewhere here. So what happens now is that there are two cases. So if you see that curve, the red curve on top, it's not exactly the maxima of the curve. It is slightly off the maxima of the curve. That's because these potential curves are not very symmetric with each other. So that maxima and this minima don't coincide. So when it has gone from this point to that point, it's actually off the maxima point. So now it has a very simple thing. It can just fall back and come back to this this point, which I'll show now. That so now it came back over here. So what happened is that when it was going from here to here to this side, it was clockwise, and then when it came back, it was counterclockwise. So this is something what was expected. It's just moving forward and coming backward. But suppose now I have another case. Now let's go back and see that what if it was still there, and now I give a small fluctuation. And where does that fluctuation come from? It's the noise in the system, because it's just in a fluid. So there is Brownian noise in the system. So what happens is that noise, sometimes there is a certain probability that it might give enough kick to the particle just so that it might go the other way and not this way. So what happens at this point is that when you go faster, you're basically escaping this normal, the route that it would have taken. It just goes up over there, and now it is at it is on an unstable point where the thermal fluctuations might either make it go one way or the other way. So in this manner, when you are going from one point to another point at a very slow time scale, you actually had a very deterministic turning. But when you are coming back, you have a probabilistic turning. It can go either way. So this will result in basically more clockwise than the counterclockwise, or either case. So this principle is actually quite quite popular. During like 1995, there were physicists who were trying to explain the displacement of molecular motors, and then they had actually coined this word called Brownian motors. So which means that if you have an asymmetric and spatially asymmetric potential, and it also modulates in time, then with thermal noise in the system, you can actually have a net displacement. So these are a few of the examples. As you can see, it is similar to our system, and this is the equation of our system, and it is similar to what there have already been in the literature before. So what did we achieve with this? So did we like actually make it more active? So we did, because if you see over here, the green curve is actually a Brownian swimmer if there is nothing in the system, and the moment you actually give an input of magnetic field, you see that there is an increase in the diffusivity. And also, as I showed in the previous slide, the turning statistics changed. Like there were too many clockwise turns compared to the counterclockwise turns. So in a nutshell, we have designed a system, an artificial system, which can be easily tuned for the activity. So it basically depends on how fast you are changing your field, and also how many cycles per second you're using, which determines your activity also. So and these kind of systems, when used in large numbers, actually give you really interesting patterns, which we are currently investigating. And then the system can also be actually the same system can be just with the time modulation of your magnetic field. You can change it from a driven system to an active system, where it can be a reciprocal doing a reciprocal motion, or a non-reciprocal swimming. Yeah, thank you so much.
Thanks, Gouri. Right on time. So questions?
I'm kind of confused by your explanation for why you get almost equal, population in the fast switching case. I mean, you talked about low Reynolds number situation. Mm-hmm. So the gravitational potential energy, which basically couples to the inertia, shouldn't matter, right?
Yeah, but here, okay, it's not. So here it is mostly the weight of this. So when it is turning, so if this is the helix, if this is the particle and it is turning, the weight I am trying to say is the weight that is basically making it turn. So what happens is that our particle is not exactly. So if I'll just show you. Yeah. So sorry here. So our part, so if you can see over in the second diagram, so when you keep a particle in the fluid like this, it always tends to go this way because of the higher weight asymmetry in the system. So the asymmetry between the weight and the magnetic moment vector here actually makes it turn either way, either this way or that way. It has nothing to, it has nothing to do with the, body's inertia in its translation motion, but it is just the weight that is basically pulling it down, what is its equal. So if the particle is just in the fluid, how will it stay over there? What position does it prefer? That is what this is.
It does not convince me, but let's talk later.
Okay,
Yeah.
Hello. Yeah, can you please explain this head part? Why you are having that?
Sorry.
Yeah, can you please explain this head part of this?
No, that is just for representation. I mean, because to make it. You mean the head part? Why it is there? No, there is no head part. It is just a helix. It is just to represent it in the diagram properly. That's
all right. Nice talk. Thank you. So are your particles tiny magnets themselves?
Yes.
Okay, and how big are they?
They are like 2 microns.
So they have their own inherent
motion in this, they do turn around like a, can I think of them as a rod shape?
Yes, they are, yeah, they are rod shaped thing, yes.
Does your switching time need to do anything with the reorientation time of the rod itself, or it doesn't matter?
No, so this doesn't matter because whatever we are giving the Z only results in this turning, and in the XY plane there is nothing. So that's why the XY orientation is completely dependent on the thermal fluctuations of the system.
Right, and with regard to the last plot that you showed of the mean square displacement, so you're shifting it parallelly to the Gaussian, to the Brownian process, right? You
Yes.
did show me the last one, the mean square displacement.
Sorry, God. Yeah.
So is it going to be ballistic or more than one at some point?
Yeah, it will be.
shorter
So
time?
after, so what we have seen currently is that's what we still have to understand. That's why I haven't shown it here. So as we increase the frequency of the actuation, so this is at lower frequencies of actuations, but when we start increasing, we see that it goes into a ballistic regime also. So I mean, we have to still understand that. So that's why we haven't put it here. Okay.
So thank you, Gouri. So our
Sorry, what? Oh, that was about the switching times that I showed when it was going from B to minus B or minus B to B. Yeah, they do. But we so we have found a way to make them stabilized by actually coating them with coating with a material which will keep them apart. But I understand you're asking whether we take into consideration that. So right now we ignore the fact that there is some interaction between them. So we work at a regime where they are dilute enough where they don't it doesn't really matter.